camaraderie. That's what it's all about. All right, so what we created is a rectangle pattern-ish. It's not really a pattern, a rectangle system. And so we're going to now patternize it. And so what I want you to be able to do at this point is just make sure that your pattern is situated in a way where you can see every single, each individual one. And try to size them so that they kind of fill up the space, but not entirely. Like, see how this one, it only has a value of I think 1 or 2 in between? I think it's only 1. So I can't go any further in my size without them touching. See, like that? I have it 1 tick down from touching. So what I'm going to do is turn these things into, I'm going to scale them, but I'm going to scale them in a gradient sort of a fashion, right? So are you guys familiar with the term gradient? Raise your hand if you are not familiar with the term gradient. Okay, it's worth explaining then. So a gradient is basically, it's a proportional relationship across a domain, in a way. So if you think about it in terms of like a shading exercise, like if this is my box and I have very little shading on one side, and then it gets a little bit more busy, and then it gets a little bit thicker, and then by the time I get to the end, it's really, really thick and it's completely solid. That's a gradient. So I did that manually, but really the easiest way is to just go to Google and search for gradient, right? Because that's what we all do academically anyway. So you type in the word gradient. These are gradients, right? It's kind of a blending between 2 different colors, if you're thinking about it in terms of colors. Anyway, so what we're going to do is scale in a gradient. So instead of it switching from one color to another, it's going to go from one size to another size. But we're not going to do it in terms of its proximity to a particular place. We'll get to that stuff later, week 2 or 3. But what we're going to do is we're going to scale it in a gradient across the list. So it'll look a little different than what you might expect, but it's going to go across the list. So here are our rectangles. Sorry, sometimes I talk really fast. And what we have to do is scale them. I'm doing a work backwards function here, right? I know that I want to scale. So I'm going to go up into the Transform tab. And it's under the Affine panel. And it's this tool right here. It's just called Scale. Scales an object uniformly, all directions. Now, this is going to request a couple things. It's going to request the geometry that it's scaling. Then it'll ask for the center point that it's going to scale it from. And then, of course, it's going to ask for a scale factor, right? So it's a multiplier that's going to tell us what, how big we're scaling it, basically, based on a factor of 1 as 100%. So the geometry obviously is going to be the rectangles. And so for visibility's sake, let's just plug the rectangles into it now and see, what it does. So here's what's happening. The rectangles are being scaled down here. I know it's hard for you guys to see the green on the screen when I select it. I've got to figure that out. I'm going to try and change that to something else. But anyway, so the scale took the entire whole construct that I built, and it scaled it down by about half size toward the origin point. Is that the default? Exactly. That is the default, yes. So the center of scaling is defaulted to 0, 0, 0. And it scaled all of that geometry based on that location. However, if we change the center point, instead of the origin, we plug in the points that the rectangles are built on, then it's going to scale every single one of the rectangles around its particular point. So I'm going to take those points and I'm going to plug it into center right there. So in the last video, was it the last video or the video before? We really discussed grafting and flattening. So it's very, very important to understand why those center points allow us to scale this geometry and why they're associated. So why do you think they're associated? Anybody? First thought, why might they be associated? What's that?
Can you repeat it?
Why would the geometry that we've plugged in, the rectangles, be able to be associated with the points that we've plugged in? Why does it work? Why are we scaling to each of those individual center points, that geometry?
Because for the points on the grid, they're scaling
Well,
the
more.
rectangles.
Maybe that wasn't the best question to ask, but maybe that wasn't the way to ask it. Actually, it was probably a poor question, so I'm sorry. But if you look at these wires, the wires are grafted. It means they come in sets. Those sets are exactly associated with one another. So when you hover over the points here, you see you have 54 items that are organized into groups of 9. And if you hover over the rectangles, you have 54 elements or items that are organized into groups of 9. If you change that relationship, it won't quite work out the way that you want it to. So I'm going to very quickly just kind of save because this might crash me, and I don't want you guys to do what I'm about to just do right here. Week 1, day 2. Oops. Thank you. So if I change that relationship, it might not exactly work out the same way. So rather than, let's say if for some reason I have a different structure to the list of rectangles. So if my rectangles are flattened into a list of 70-something rectangles, or 54 different rectangles. So now what's happening is I'm taking 54 rectangles and I'm scaling each of those 54 rectangles to each of the packs of 9. And so what I actually get are 324 rectangles, all in different weird spots. Okay, so just be aware that the data is going to build really fast. You need to just... The reason I'm taking such an excruciatingly long time to explain lists is because the longer I spend explaining them to you, the less frustration it's going to mean for you later on when you're troubleshooting. Okay, it's worth our time now. Okay, so anyway, going back here, the things match, and so we've scaled it down. So now it's the scale factor. Yeah, I'm going to try to do this part pretty quick. Yeah. So the scale factor, right? We are now operating off of domains, right? Minimum and maximum values. So what happens if I want to create a gradient, right? A gradient is basically establishing a minimum and a maximum value. It's a boundary that says I want to create everything in between this boundary, or a number of things in between this boundary. So I can create a list of scale factors between one number and another. So if I go up to set and sequence, I don't know if I want range or series. Probably series. So I always forget what the difference is between range and series, because range creates a range of numbers and series creates a series of numbers. It's pretty much the same. So this has first number of the series, step size, and number of values. Range has the domain. So range is domain based. Okay, yeah, that's right. So that's the one I want. I want range. So range is kind of a way for you to define using a domain and just basically breaking up your minimum and maximum value and saying, I want this many things in between. So, or this many numbers in between. So the domain is going to get plugged in, and so we have to construct a domain for it. So let's go to math and domain, and let's construct a domain. And I'm going to move this up here for clarity, just to kind of keep it a little bit more organized. So anyway, I'm constructing a domain. I can use static numbers. I can use a slider if I want. In fact, I will use a slider just to show you the dynamic nature, but feel free to use a static number if you want. Anyway, so A, B are just my two different numbers. So I'm going to do a slider from 0 to, what are my numbers down here? I have 3, I think, is my highest value. Oh, wait. Okay. So this is my 100% value. I can't go above 100%. Or I could go slightly above 100%. It depends on what value you have here. So the original rectangle here is my 100% value. So I could probably go I could probably go up to 150%. So that would be a 1.5 as my maximum. Does that make sense? Well, you'll see. Anyway, so I'm going to do a slider from 0 to 1.50. 0 to 1.50 because I want it to be a smooth, 2 decimal place precision. So copy that down, and I'm going to put 1 in A and 1 in B. And then the only other thing that you need to be aware of is that you need to give it the number of steps. So the number of steps can be read off of the list length. Now this is probably one of the first instances where we're kind of taking an idea from one and we're sort of inputting it into a totally different other idea, right? So the list length now we can use in this case as well. So the list length is basically going to be the number of points. I'm going to go to set and list and use list length. I'll measure the number of points and I'll plug it into n. Also be aware that that number of points needs to be flattened. Notice how it's coming into n as a bunch of groups, and so what it's reading on the n input is 6 values. That's not what we want. We want the list length to be read as flattened. Make sure that you flatten it as it's going into the list length. Otherwise, it's still going to read your individual groups. Any confusion about that one? Okay. So we have a range. We have 55 numbers, 0 to 1 point whatever. What did it go to? 1.19? Oh, because I only put it up to 1.19. So I'll go to 1.5, right? And it changed that list. Now it goes all the way up to 1.5. So I have 55 numbers. I'm going to plug those into the scale factor. Oh, it gave me an error. Why is it giving me an error? Oh, I know why. So you can't have a scale factor of 0 is what it told me. So go ahead and pull it up slightly off of 2. And what you're going to notice is that it's not really reading properly, right? The pattern is all being applied kind of to this top row. Why do you think it's only being applied to the top row? Recurring themes here, right? What's that? Right, it needs to be flattened. Very, very good. So the point output, pretty much at this point, if you're doing a pattern across a straight list of numbers, right, you want to make sure that that whole list of numbers is flattened, right? Because the gradient is based off of the relationship of its entire striation, right? So it's not a row or column-based thing. So this entire list of points needs to be flattened. Also, so the rectangles automatically get flattened with that. So we're going to need to turn a few things off in order for this to make sense. Right now we still have our original rectangle showing. We also have the grid showing, so I'll turn that off, and this is what you see. It's a pattern gradient. Any questions about this right now? So I very, very quickly, I know this video is getting quite long. I don't like to run them this long, but I wanted to get the whole idea in one thing. I very quickly want to point out this error. So you'll see that the list length created, using range, it created 54 numbers, or rather it says the number of steps, right? The number of steps means basically the gap in between numbers. So rather than creating 54 numbers itself, it's actually creating 54 places in between, which means 55 numbers. So I have one extra value. So at the very end here, it's actually creating the very last item is just put in the same place. So if it matters to you in that definition, you have to basically just subtract one number from that list. And so you can shorten the list length using math. You don't have to do this right now, but if you want to get it measured in yours, just do go into math and operators and do a subtraction. And whoops, put it in the top, and then subtract a static value of 1. And then plug that into your n, and now you don't have that error anymore. So why is this super cool, right? The gradient is fully malleable, right? I can change my minimum domain. So now I have the ability to just kind of, lower the relationship here. I can make it, reversed. I mean, I think that's pretty cool stuff. I don't know about you, but that's pretty cool. All right, so I don't hear any questions coming out from you guys. So what I'm going to do is stop this video here. We'll go on another quick break, then we'll come back and do some other cool stuff.